converting Cartesian complex numbers into modulus argument complex numbers. So if I have the complex number z, and it is equal to a plus bi, where a is your real, b is your imaginary, then z in modulus argument form is going to equal the square root of a squared plus b squared. Notice I don't have the I, so a squared plus b squared times the cosine of the arctangent of b over a, no I again, plus I sine the arctangent of b over a You'll often see this abbreviated as cis, which just means cosine plus I sine. So z is going to equal the square root of a squared plus b squared times cis arctangent of b over a. And we have the arctangent. Remember always to consider what quadrant you're in. So here I have positive A, positive B, negative A, positive B, negative A, negative B, positive A, negative B, and then your respective quadrants. So now I'm going to run through an example. I'm going to say, let z, the complex number, equal 1 minus I. And how would I express this in modulus argument form? So just how we did previously, z is going to equal the square root. Let me just quickly. A is going to equal 1, B equal to negative 1, 1, negative 1, the real and the imaginary. Square root of a squared plus b squared, so 1 squared plus negative 1 squared times cis of the arctangent of negative 1 over 1. This is just negative 1. And so now we have to think about for which value, or for which angle value, does the tangent equal negative 1. And so if we draw out our argument-plane here, and this is our imaginary axis, this is our real axis. If A is positive, that means we're in either quadrant 1 or 4. And B is negative, meaning that we're in quadrant 4. So tangent is negative 1 at 7 pi over 4. So z is going to equal square root of 2, 1 plus 1, cis of 7 pi over 4. And if we want to verify this, see we did it correctly, we do z is going to equal the square root of 2 times the cosine of 7 pi over 4 plus I sine 7 pi over 4. Z is going to equal square root of 2 times the cosine of 7 pi over 4 is the square root of 2 over 2 times the square root of 2 over 2 plus I, just distributing the square root of 2, square root of 2 And then the sine of 7 pi over 4 is negative root 2 over 2 times negative square root of 2 over 2 z. So the square root of 2 times the square root of 2 would just be 2. It's going to equal 2 over 2 plus I. Square root of 2 times negative square root of 2 is going to be negative 2 plus negative 2 over 2. Z is going to equal, anything over itself is just 1, so Z is going to equal 1. Negative 2 over 2 is negative 1 minus I. And that goes back. So now you might be wondering, but why does this work? So if I have Z equals A plus BI, coming back to this, I'm going to draw the argand plane. Draw this out here. Do that over here. So here I have the imaginary axis, and here I have the real axis. Now I'm going to plot Z on my plane, just a generic complex number. Right, because A is my real aspect, and so it is X, and then B is my imaginary, which is why it's on the vertical axis. And so often you'll see complex numbers like these plotted as vectors, lines, like this. So that's what I'm going to do. Right. And I'll just call this length C. Okay. Which would make this height B and this length A. Okay. And so the angle between this line right here and the real axis, I'm going to call theta. And so the tangent of theta is going to equal B over A. Now I'm going to take the arctangent of both sides. And taking the arctangent of the tangent of an angle is just going to leave you with the angle. And I'm left with the arctangent. Hopefully this looks familiar. Theta is going to equal tangent, arctangent, B over A. Great. Okay, so now I'm going to try to express I'm going to try to express Z in terms of theta and C. So the sine of theta is equal to B over C. Solving for B here, B is going to equal C sine theta. However, it appears as BI in our complex number, so I'm going to express this. I'm just going to multiply both sides by I. And so BI is going to equal IC sine theta. I'm going to do the same thing with cosine of theta. I'll do it in a different color. The cosine of theta is going to equal A over C. So A is going to equal C times the cosine theta. Great. So now looking back at our complex number Z, A plus BI, now I can substitute. So if z is going to equal a plus bi, then z will therefore equal a c cosine theta plus bi, and we've said bi equals this. So plus pi c sine theta. I'm going to factor out c. And as I previously mentioned, cosine I sine theta is often just expressed as cis. So z is going to equal c times cis theta. But what is c equal? Well, this is a right triangle here. And so we can do c is going to equal, just by Pythagorean theorem, c squared is going to equal a squared plus b squared. C is going to equal the square root a squared plus b squared. Notice no I. And so that means that z is equal to the square root of a squared plus b squared cis theta. As I previously mentioned, theta is going to equal arctangent of b over a. So z is going to equal the square root of a squared plus b squared times cis of the arctangent of b over a. And there we go. Now if you're ever asked, say you see, for example, you're taking a test and you see argument of z, and z is a complex number, the argument of z is simply equal to theta, or arctangent. And if you see, I don't know how they abbreviate it, but the modulus of z, that's just equal to the square root of a squared plus b squared. So this is going to equal arctangent of b over a. And this is going to equal the square root a squared plus b squared. There you go.